Hey guys, how's it going? So today we're going to be doing something called the Fundamental Theorem of Calculus. And it's a really important principle taught in Calculus 2 that basically strikes the core of calculus concepts. Why is it called the Fundamental Theorem of Calculus? I'm going to say the reason why it's called this. It's because it is connecting the concepts of differential calculus and integral calculus. Differential calculus and integral calculus. And like differential and integral calculus are the two fundamental concepts of calculus. You use them later on in multivariable calculus, vector calculus, complex analysis, you name it, these two concepts are there, basically. And the fundamental theorem of calculus connects these two calculus points together. So there's a differential part, first of all, the part one, that says if g of x is equal to, I'm going to draw it, if g of x is basically equal to x from a to x, where a is a real number, f of t dt then what that implies is g of g prime x, the derivative of g, is just equal to f of x. That's the first part of that's basically the first part. Secondly, you can use a concept of antiderivatives to find the area under a curve, basically. So here, let me write, this is better if I just draw it out. From, let's say, from 2 points, from A to B, and then f of x dx, like you're trying to find the area under a curve, then the value of this integral or area is just equal to f of b, capital F of b, minus capital F of a, f is any antiderivative. So you might find occasionally 2 or 3 different antiderivatives at times. It doesn't matter. Any antiderivative would work, and then you can subtract b from a. No, a from b, yeah. So f is any antiderivative. Yeah, deriv. So yeah, these are the two main concepts of the fundamental theorem of calculus. So let's without further ado, let's go down. Let's dig deep. I'm the kind of guy who likes to learn by doing, and I teach by example. So why don't we show you guys some examples here. So here's our first example. Let's say f of x, we're applying the first concept of the fundamental theorem of calculus right now. So f of x, let's say it's the integral from 2 to x, t squared plus 2. dt. Okay, so what is f prime x? Well, applying this f prime x concept here, g prime x is just f of x. What we do is just simply swap out the t variable. So f prime x would just be x squared plus 2. So it might sound a little confusing at first, but I just want you guys to like understand here. So like, first of all, understand the concept and model it here. So a is some number, constant number, all the way to x. F of t, which is t squared plus 2 here. I should have said g of x, but it's just a letter, so don't worry about it. So then g prime x here is just equal to f of x, where we swap out the t with x. And before I continue, bear in mind that as long as a is any constant here, this works. So if it's 0, 1, 2, 3, 4, then f prime x will always equal x squared plus 2, as long as this was in the lower part of the integrand. If we had something like this, so let's say f of x is, if it was 2, no, sorry, what if it was reversed? Like, let's say from x was down here, so from x all the way to 2, and then the same function t squared plus 2 dt. You're just going backwards. So anytime like, then the derivative would just be a negative. Would be negative x squared plus 2. And you're going to see this later, like in the second part of the fundamental theorem of calculus. Let's say you're going from 0 to 4. If you're going from 4 to 0 of the same curve, then that value is negative from the original answer. Yeah, so when you swap the values for the boundaries, then just change the sign, essentially. Okay, so that's the first example. The second example, let's try h of x is equal to, and because it's a new example, obviously the scenario will be different. Otherwise, what's the point? H of x is equal to, let's see, what do I want to do here? 2x squared. Wait a minute, I planned a bunch of things here. So you know what? Let's do it. 2x squared from 1 to 2x squared, t to the power of 4 plus 1 dt. But we're still applying the first concept of the fundamental theorem of calculus, but we need to be a little careful. So I'm going to directly write the answer first, and then I'm going to explain my answer. So h prime x. So first of all, apply the 2x squared, substitute 2x squared into this function g of, into f of t, or t to the power 4 plus 1. So substitute that in, so you get 2x squared to the power 4 plus 1. But we're not done yet. We need to multiply this because it's not just a straight x. We have to use the chain rule. So we're going to have to multiply this by 4x, because 4x is the derivative of 2x squared. And if you want to simplify this, that's just 4x times 16x8 plus 1. So basically, if it's x, you can just directly sub x for t. If it's not just x, then you have to like substitute this variable inside t and then use the chain rule and find the derivative of this top integrand. Let's do one more. So g of x is equal to Okay, so we're gonna, this time it's gonna be sine x to e to the power of x. 6, 6 sine x to e to the power of x of t squared dt. Now, this time the bottom part, the bottom boundary is not constant. So we cannot so we have to be a little careful. What I recommend doing is breaking it up. So whenever you have something where the bottom boundary is not a constant, what you can do instead is something like this. Watch. E to the power of x, 0, t squared dt. Just say it's like make the bottom some constant, minus sine x from 0 to sine x. Sorry for the way I drew the sine x, guys. T squared dt. And intuitively, this kind of makes sense. I'm going to make a side note for this over here. So it's like, imagine you had a curve that with your x and y, it looked something like this. And then let's say this was x and this was some constant c. If you had something like d here, then basically, let's say you were trying to find the area of I don't know, d, something like this here. But then you could just basically say the integral, the area, would just be equal to, if you just wanted to find from d to x instead of c to x, then what you could do is just say from x to c, f of x, sorry guys, from c to x, yeah. From c to x, f of x dx. So this area minus from c to d, this area minus from c to d, f of x dx. So that's the concept I'm applying here. So this is not easy to solve directly, so we just set the lower bound to 0 in both cases and do this here. Yeah. And I'll leave this. So I'll erase this part later. Okay, so now we can separately figure it out and apply concepts we learned earlier. So here, that sub e to the x directly in t, so that's e to the 2x times e to the x, because remember the chain rule, minus sine x, so sine x, so let's see, sine squared x times cos x. Because remember, sine x times to the power of 2 is sine squared x, and then derivative of sine is cos. And you can just say this is e to the power of 3x. I'm lazy. I don't feel like doing it. I'm going to leave this as my final answer. So hopefully this gives you some idea of the first part of the fundamental theorem of calculus. If you don't know, guys, just let me know in the comments section, or just simply email me and I'll do more examples of this. So yeah, that's the first part. Let's do the second part. It seems kind of abstract, the first part. I still don't entirely get it, but this is one of those cases, the first part, it's better you do a lot of examples of it. That's all I recommend for you guys, seriously. So yeah, part two, basically, I want to like visualize this with you guys first. Let's do an example. Let's do something like this. So basically, let's say we're trying to find the area from 0 to 4. Sorry, what? Let me think. 4 minus x dx. Sorry, 0 to 3. 4 minus x. Sorry, guys. I'm gonna. I'll be back in a second. I want to see if my example was accurate. Hey guys, I'm back. Never mind this example. I have an even better example. So basically, let's say right now we wanted to find an area that's bounded by two curves. Okay, let's say an area bounded by two curves. Area particularly bounded by y equals x squared over 2, or 1/2 x squared. And the second one is x plus y minus 4 is 0. Or like, I think y equals 4 minus x. So how do we go about this? If you could try solving this, visualizing this in your head if you want. Or if you're not that great at visualization, you could just graph this. This is not the most prettiest graph, but if you do graph it, it looks something like this. Get out some graph paper, maybe a ruler so you could draw straight. This diagram is not drawn to scale like always. Yeah, looks something like this. And like you could have like visually seen, maybe if you drew it to scale, you would have seen that this point was x equals 2, y was 2 here. And I think this part, yeah, no, this is y is 8 and x is -4. And of course, this is 0. So then the 2 points of intersection are -4, 8, and -4, 8, and 2, 2. These are the 2 points of intersection. I'm going to draw that, yeah, 8 and 2, 2, yeah. So what we do now, applying this, it's pretty obvious from here that the part y equals 4 minus x. I'm going to write it down just so I don't forget. The y equals 4 minus x part is constantly above y equals x squared minus 2 from x equals -4 to 2. You have two ways you could solve this area, finding this area. You can either find the area separately with 4 minus x subtracted by x squared over 2, or you can just do them together. I'm going to do them together. So here we have a is equal to, from -2 to 4, four minus x four minus x, okay, subtracted by, because that 4 minus x is the higher of the two curves, x squared over 2 dx. And that is equal to So 4 minus x squared over 2. Just simply take the antiderivative of all this. So the antiderivative of 4 is 4x. The antiderivative of negative x is negative 1 over 2x squared. And for negative x squared over 2 is negative 1 over 6x cubed. Yeah, from negative 2 to 4. The area, the shaded area where I did not very neatly shade, that looks like a French mustache. Maybe that's a good idea for a video. Actually, hold that thought. Okay, so from negative 2 to 4, this is the antiderivative. We don't have to include c when you're doing the second part of the fundamental theorem of calculus, because it could be any antiderivative. So let's just set c equals 0. So from negative 4, so capital F of 4 minus capital F of negative 2. Okay, so capital F of 4 times 4 is 16. 16 minus 0.5 times 16, that is 8. 8 minus 1 over 6 times 64. So 8 minus 64 over 6, or 32 over 3, minus capital F of negative 2, negative 8 minus 4 over 2, that's negative 10. Negative 10 minus, let me think, negative 1 over 6 plus 8 over 6, sorry. Okay, negative 32 over 3 plus 4, negative 2, sorry, 18. Sorry, guys, I'm going to be right back. I want to see if my calculation is correct. Okay, so I briefly checked my answer. The answer is actually 30. I already did this before, so I would know. Yeah, the answer is just 30. You could solve it out yourselves. Okay, I have one more example for you guys before I end the video for today. So let's erase all this. Okay, so let's, this time, this is not your typical integral question, but let's say you have something from 1 to 2, f prime x dx. And let's say this is equal to 2 from 3 to 5 f prime x dx. Furthermore, we know for a fact, I'm giving this to you, that f of x intersects the following points. It passes through 1, 2. It passes through 2, 4. It passes through 3, 5. And 5a. So f of 5 equals a. what is the value of A? So applying the fundamental theorem of calculus here, okay, first of all, I'm going to say what is A, like this. So keep our goal in mind. So we first of all apply the fundamental theorem of calculus part 2. The antiderivative of f prime x is just f of x. So here that means f of 2, b equals 2 here, and a equals 1. F of 2 minus f of 1 is equal to 2 times f of 5 minus f of 3. And here because of this, we now know what f of 1, 2, 3, and 3 are. So f of 2 is just 4, and f of 1 is 2. So 4 minus 2 is equal to 2 times a, because f of 5 is a, minus 5. And when you solve this, a is equal to 6. So yeah, that's all the examples I have for you guys today. I hope this was a very enriching lesson, and I hope to be back with more. I'd love to stay, but for now, I gotta jump. I'll see you guys on the other side of the bridge. Catch you next time.